Hello and welcome to this tutorial on the induction motor at startup. What we're going to look at here is we're going to look at how the machine is behaving when it is first turned on in its startup condition. And to do that, we are going to be using the equivalent circuit that we derived earlier in the previous tutorial. And we're going to use that equivalent circuit along with some information that you can get off the nameplate of the machine. So let's start with some things that we can assume or know about the machine. So the first one we're going to look at is the line voltage. We'll say that that's 400 volts, and the rotational speed of the machine is rated to be at 1450 RPM. The frequency is 50 Hertz. It's a three-phase machine, obviously. We'll say the number of poles is 4, and R1 is 0.25 of an ohm, R2 is 0.2 ohms, X1 is 0.5 of an ohm, X2 is also 0.5 of an ohm, because you'll remember from the tutorial before, those two are usually the same. In these models, it's assumed that they are the same. And we'll have XM as being, it must be much larger, we'll call it 30 ohms. So there are several things we can do straight off the bat here, which we're probably going to need later on. The first one is if the line voltage is 400, we therefore know that the phase voltage is √3 times that, so that'll be 230 volts. We know that the rotation speed at 1450 RPM is the same as 151.8 radians per second. We can't do anything simpler than that, so that's fine. What we can do is we can work out the synchronous speed, because we're going to need to know that. Synchronous speed is 120 times the frequency over the poles, which is 120 times 50 over the number of poles. This is a 4-pole machine, so that equals 1500 RPM, which is the same as saying 157.1 radians per second. Now, normally we would want to know what the slip is in the machine, but the purpose of what we're doing here is we're looking at startup. And we know that the torque response for a induction machine looks something like that. And at this point here, this is the the synchronous speed, where in this case is 1500 RPM, and we know that at that point there, the slip equals 0. We also know that at this point here, where it's 0 RPM, the slip is 1. And that's important because that's what we want to know. This whole problem that we're going to be doing is solving the startup when the slip equals 1, and that's going to be handy later on. Because if we go back to our equivalent circuit is R1, X1, XM, X2, and R2. And in this particular case, R2 is 0.2 ohms, X2, X1, XM, and R1. R1 is 0.25, X1 is 0.5, 0.5, XM is 30. We know what the input voltage is, we don't know what the current is. So if we want to understand how this machine is going to work at startup, we do want to know what the input and the startup current is. That's going to be one of the things we're going to need to know. We know what the voltage is, but we don't know what the impedance is, so we need to find that out. So we can start with that. The impedance of this circuit is these two in series, which are in parallel with this one, and then all of that is in series with these two. So starting from with this, the impedance of the circuit will be R1 plus JX1 plus, because it's that, all of this is in series with these ones here, which will be JXM times R2 over S plus JX2, and all of that is over R2 over S plus JX2 plus XM. And we can go through and put some values on that. So R1 0.25 plus J 0.5 plus JXM is 30 times, and this is the first thing that makes life a little bit easier for us, 0.2 over 1, because as I said we've deduced slip is 1, plus JX X2 is 0.5, and that is over 0.2 over 1 plus JX2 0.5 plus XM 30. Now I haven't got enough paper here to go through and do the full simplification, but what I will do is I'll skip a few, and then the line that I'm going to put down here is not quite the final simplification, but it's one that tricks a lot of people, and that is that line simplifies down to (0.25) plus J 0.5 plus J 0.49 plus J, well, it's actually minus J 0.19. Now, a lot of students at this point here will see these J terms and they'll just go and add this one plus this one plus this one, even allowing for the fact that this is a negative. That's not correct, because there's something going on here that a lot of people overlook. And if you did that, you would say, if we make these squares down here, each of these squares is a quarter, and the real axis, if we say the real axis is in this direction, we would be going 0.5 plus J 0.5, so that would be 1, 2 up here, plus another 0.5, and then minus close enough to 2. So they would come back down here, and they would say that this here is your solution. That's wrong. The reason it's wrong is because they have overlooked what's happening here. What's actually happening is you go there for your 0.25 in the real direction, and then yes, you'd go up 0.5 in the imaginary axis, but this term here actually applies to this. So we continue like that, but this minus J, this term here continues to be in the imaginary axis, but this one here is perceived as being as though we've reorientated the real to being in this direction, and so this one now doesn't go back down this way, it goes this way. So this one here, if we call this term 1, term 2, term 3, and term 4, this is term 1, this is term 2, this is term 3, and this is term 4 here. So our end result is actually that. So that means when you actually do that, you end up with a solution that looks like, and you actually do the math properly, 0.44 plus J 0.99. And that's what you see down here. Okay, and so that's our impedance, and that there in polar form is 1.09 at 65 degrees. Once we understand the impedance, we can now work out the current. And to know the current, Ohm's law, voltage, Ohm's law says voltage equals IR, so we can rearrange that. Our current is going to be our voltage over our impedance when slip equals 1. So that is, and we're using a single phase model, that's our line voltage. This is a single phase model, so we need to use this number here. So that's 230 over our impedance, 1.09 at 65 degrees, which gives us a current of 212 amps at minus 65.9 degrees. A large current, a very large current, and not surprising. So, if we need to, if we also want to find out, we know the speed here, we know the slip here. We've found out the inrush current here, but what's our starting torque? What's this number here? We know that torque is, sorry, just a slight distraction there. We know that torque is power over rotation. We've got this value. Do we have this? We don't. We don't know how efficient the machine is. We don't know what its input power is, its output power. We don't know this, so we need to find out this sort of information. So we do have the rotation speed here of the rotor. We've got the resistance of the rotor. We don't have the current flowing through the rotor. But we can find out what that current is because we know what these impedances are. In order to find out what this current is, we need to know what this voltage here is. This voltage here, which is called E. We'll call that E. And once we know that this voltage is, we will know what these impedances are, then we can calculate what this current is. So the voltage here is this current, this voltage less the volt drop across here. To find the volt drop across here, we need to know what the current is through here. We know what the current is through here because we've just found it. Here it is here. So we can take this voltage, find out, drop this voltage over it, this volt drop over it, and then that'll give us the value of E. So this voltage E is our input voltage minus the volt drop across here, which is the primary voltage, this current that we've just found, times R1 plus JX1, which is, this voltage is 230 minus our current flowing through, which we've just found out down here to be 212 at an angle of minus 65.9, and that is going to be times R1 0.25 plus J 0.5. And if we go through and reduce all that, and as you can see I'm running out of paper, so I'm not going to do it for you, that resolves down, and that will give us a voltage here of 112.4 J, or minus J 5.18, which is the same as 112 at an angle of minus 2.64. So we now have this voltage. Now that we've got this voltage here, we can then go and find out what this current is. And using Ohm's law, the current, our secondary current, our current down through here, is going to be V equals IR. I is V over Z, so it will be, the current down through here will be the voltage divided by this impedance, which is R2 over S plus J X2, which is 112, wrong voltage, at minus 2.64 over 0.5 plus J, 0.2 over our slip of 1 plus J 0.5. And that simplifies down and gives us a solution of 208 amps at an angle of minus 70.84, which is the same as saying 68.5 minus J 197.3. So we now know what our current is. From our current, we can then start solving this, because we know that our torque is P over the rotational speed, and P is I squared R. And this is total torque for the machine, and this is a single phase model. So our torque is 3 times our current in our rotor times the rotor resistance over S, and that's squared because it's I squared R, and that is all over our rotational speed, which is, so that gives us 3 times our current, 208 at minus 70.84 squared times our value of our resistance, which is 0.2 over our slip, all of that over our rotational speed, which is 151. And that gives us an answer of 172.4 Newton meters. That's pretty much about there. There is one other thing we could look at. We know the power factor for this. Power factor is cosine of the angle. We know the angle. Here it is over here. It's 65 degrees. There it is. So that would give us it's a cosine of minus 65.9, which gives us a power factor of 0.408. So that is how we can understand what is happening in the induction machine at startup. We've got what is effectively our inrush current. As soon as we turn the machine on, this machine is going to draw 212 amps. That's a lot, right? And it's going to do it with an absolutely appalling power factor of 0.4. We found that that number here is going to be 172 Newton meters. This is the torque in the machine when it has 0 speed, because slip equals 1. This appalling power factor, most of this current, as we can see, the current that we are drawing, we have found to be 202 amps. Most of it is going straight into the rotor. Okay, magnetizing current is quite small at this stage. All that energy is being dumped straight into the rotor. We've got a very large volt drop across here, because if this is 230 here, and this voltage here we found to be 112, so we've got a very large volt drop across here. This is a very interesting revelation, because all these numbers are realistic. I haven't made any odd numbers. This very bad power factor shows that the induction machine at startup have very bad power factor. I'll be doing another tutorial on a very similar process when the machine is running at rated speed, and we'll find out what's going on down here at this point here at the rated slip point. But this is what the machine does at startup. Thank you for watching. I hope you learned something. I look forward to seeing you again.